The idea of a special E-Days lecture was not something that last year for particle physics I actually covered something because I was reshuffling the curriculum, and I covered like CP, C, and CPT invariants, which led into this discussion about the baryon symmetry of the universe, but then just for shits and giggles we talked about the monster group. But anyway, because it tied into monstrous moonshine, and not that moonshine had anything to do with what was going on. But anyway, so we're all going to be well behaved today. I hope.
I believe you.
Yes. And I'm going to very quickly start with the last bit of what I was going to talk about last time. And then we're going to go into today's topic, which, trust me, you will all be very glad you came to class today when you see what we're going to talk about. So I'm going to very quickly redraw the light cones using Eddington-Finkelstein coordinates. And we found, yes, that noise is so annoying. I don't know what it is, but I hate it. So what we found was that there were inward going light cones which corresponded to one set of solutions. Those are all supposed to be at 45 degrees. I'm a little lazy right now. And then you had the outward going light cones. And then what we discovered is as you start approaching the horizon, those inward going light cones actually tip over, and then at the horizon they actually go straight up, and then beyond the horizon the light cones actually, I don't know why I did dashed lines instead of solid lines, that was stupid, but anyway. So our light cones tip over, and that's why everything inside of a black hole's horizon has to go towards the singularity. Okay. So what I'm going to do now is use a similar picture to talk about what an external observer sees when something that they know and love falls into a black hole, which we all now know we can videotape because we have pictures of black holes. So, but we're going to reproduce a familiar result. I don't know why I just erased why did I draw that up there if I was going to turn around and erase it? It's not going to be a good day, I can already tell. And now I haven't had anything. Shut your pie holes and learn. Okay. So, well, I am strangely drawing stuff that I just erased.
Are you sure you haven't had anything today?
I'm very, very sure. I just came from a faculty meeting. I'm pretty sure I would not do anything stupid. Okay, so starting at our star, well outside of the horizon, okay, where the light cone might look like that, what we're going to do is we're going to have an object that's going to go into the black hole. So it is going to follow some trajectory inside of the light cone, always within the light cone, and eventually find its way to the singularity. Okay? So as this thing falls into the light cone, as this thing falls radially inward past the horizon to the singularity, we're going to have U sitting at a constant fixed value of R. Okay? So this is you, and this is your friend. Okay? You are happy, and your friend, who probably had a little too much, is happy too. But as your friend evolves, when they pass the event horizon, they're still happy because nothing really bad happens at the event horizon. They are still just as happy as they can be, but we're all aware that when they hit R equals 0, they get rather unhappy. They actually get unhappy before that because the tidal effects will actually rip them in two, or rip them into many pieces like spaghetti, but they're definitely going to be dead by the time they hit the singularity at the center. But what we want to do is we want to consider your friend actually sending you signals as they fall in, okay? So they're going to, on a regular basis, send out light pulses to you. So these are regularly spaced according to your friend's stopwatch. Okay. And then each of those light pulses is going to be aimed radially outwards, but of course it's going to follow the edge of a light cone. Exactly. So for the first pulse is pretty much just going to be a good old normal light cone. But then as the person gets closer and closer to the horizon, what we discover, as we know, is that the light cones, and this is a really bad illustration of this, I realize it. God darn it. Man, I screwed this up already.
Should those be curved?
They should curve because that's actually a very good question. I'm glad you asked that. It's almost like I told you earlier to ask that, and then you're coming in here and seeding a really good question.
You definitely did not do that.
Yeah, I know. Totally know. Okay, I'm going to explain to you why they should be curved in just a second. God, this is so hard. Yes, and then Okay, why are they curved? That's a good question. So the light, let's take this one. When the light leaves this point, okay, it can move radially outwards. So it can move to a larger value of r, but because this point is very close to the horizon, this edge of the light cone is steeper than 45 degrees. It's 45 degrees when you're far away, but the closer you are, it's closer to vertical. However, as this thing moves, it gets further away, so the slope has to eventually relax to 45 degrees. So that's why they're curved, okay? Now, the important observation here is that if all of these are released at the same time interval, which I'll just call delta tau, okay, the reception is actually growing in time. And if I had drawn the picture more accurately, the picture in my notes is a much better illustration. But the idea is that the received signals are getting further and further spread out in time. Okay? So, in fact, you'll never actually see the signal emitted at this point. Okay, because that signal just heads straight up the event horizon. Alex?
Is that considered an orbit of the light when it's emitted at the event horizon?
No, it's literally, it's not moving in all angular motion the angular dimensions are suppressed and angular motion is non-existent. So you're literally aiming the light straight out, but at the event horizon it just sits there. Yeah. Weird. Okay. Anyway, so now let's go back and let's just say, instead of your friends sending signals, let's just think about the light coming off of them. Okay, you're emitting light, you're emitting black body radiation. So so we can imagine the light coming off, and we are receiving the peaks of the light. Okay. Well, what's happening to the wavelength, or actually what's happening to the frequency of receiving the peaks as the friend gets closer and closer to the horizon? So the frequency decreases because the time between peaks is getting larger and larger and larger. Okay? So as your friend falls into the black hole, what happens to the color of the light that you see emitted from them? It redshifts. It redshifts. In fact, your friend redshifts away. So it's really interesting because on your friend's, so this is really interesting, on your friend's clock, so their clock is just ticking at these intervals. They just cruise right through the horizon in a finite time, and they end up at the singularity in a finite time in their experience. But from your experience of watching them, what you see is that they basically asymptotically approach the horizon but never pass through. Which always bothered me because the first time I took a general relativity course, somebody said that, like they approach the horizon but they never get there. And so I had this picture in my mind of like your friends going into the horizon and then they just kind of freeze. And that's what you see for the rest of your life when you look at the black holes like your friend. But no, it's simultaneously that they slow, this is what you see, they slow down but they also redshift away. Okay, so they fade away. So it's not like you've got this permanent fixture of your dead friend on the horizon. Yeah, go ahead.
Does the duration of the light pulses also increase in time then?
What do you mean the duration?
Like if they're sending out light pulses that are on for a certain amount of time, I guess, then the redshift away, did the duration of those line pulses get longer from your perspective?
Yes. Yeah. I mean, all time intervals. The time intervals associated with your friend are just going to be elongated as you observe them. Whether it's the duration of a light pulse, whether it's the time between light peaks of a wave, or whatever. Okay. All right. This is a redshift effect, and you're all familiar with the idea that you have a redshift effect in special relativity, or hopefully you're familiar with that. And you'll notice that in this context, it's a redshift effect from two things. One, from the motion, but then also you have an additional redshift effect coming from the geometry itself. All right? So general relativity is really cool because it automatically includes the effects of special relativity. I mean, special relativity is in general relativity, okay? But it includes on top of that extra effects, and this is something which you'll see explicitly when you do your final exam. All right, on to the cool stuff. Let's do the following. I'm going to consider a spatial geometry. This is purely spatial, no space-time yet. That is going to look remarkably simple. It is a space-time geometry. I just totally lied to you, but that's okay. So it's got a dt squared, an r squared, and then a d theta squared plus sine squared theta d phi squared. Okay?
Should I need a dr squared? Particularly isn't it so far away from the other?
Oh, no, wait, hold on. Jesus. H. Snazzy puff.
No.
Yeah, wait.
Right.
Yeah, no, it should be a dr squared. I don't know where I dropped that dr squared. Hold on a second. Yeah. I'm going to have to go back and correct my notes. This was woefully wrong. Okay. Yes, just ask.
What's it called? If you're on the inside of the event horizon, do you see them twice?
If you're on the inside of the event horizon as your friend is perilously falling to their death, would you see them twice?
Yeah. Like once they cross the event horizon, then both light cones are like this.
So if you could sit still to the side of the event horizon, like the two light cones would reach you eventually. Yeah. So you'd see two images, right?
I'd always be pointing.
Well, there is a question of whether you're moving faster or slower than the light cone edges. Because one of those light cone edges is radially outwards, one of them is radially inwards, and you're somewhere in between. Okay. If you're inside, if you're inside, you're not hanging out waiting. You're heading towards the center too. Okay. Okay. What space does this describe?
Spherical.
Say it loud. Say it proud.
Spherical Minkowski space.
It is Minkowski space in spherical polar coordinates. Okay. It is an absolutely, utterly, completely, and totally boring space. We're going to jazz it up. You ready? I know. Super sexy. We added a plus b squared. I know. The consequences of that are about to blow your mind. All right. So it helps whenever we write down non-trivial metrics to specify the ranges of the coordinates that we're dealing with. So that b is a constant. And for our coordinates, we have in mind that t takes the usual values from minus infinity to infinity. The radial coordinate runs from 0 to infinity. Theta goes from 0 to pi. And phi goes from 0 to 2 pi. And the round and the square brackets are intentional if you don't know what those mean. Phone a friend. Okay, so I'm going to make some initial observations about this geometry that are very useful. It's time independent. T does not appear anywhere. And there is no dt dxi cross term. Colton, if there's no time involved in the metric coefficients, what kind of geometry do we call it? So if the geometry doesn't evolve with time, what kind of geometry do we call it?
Stationary.
Stationary, good. If there's no dt dx or dt d spatial cross terms, it's additionally
Static.
yeah, because what do these cross terms, if they're there, give you? So if you have no t dependence, but you do have a cross term in dt d spatial, what happens when you switch the direction of time?
Oh, it's that time period.
Well, you get a negative sign if you switch the direction of time. So we talked about a cross term like this describing a spinning object. Okay, so Dylan, when r goes to infinity, what do you think this geometry is going to asymptotically approach? B is a finite number.
Is it going to be like Cartesian? Or?
Yeah, Caleb's helping you.
Flat.
Yeah, it's going to approach flat space. Because when r goes very, very, very large, b basically becomes irrelevant. And then as Madison pointed out at the beginning, that's just the metric of flat space. Okay? So if r goes to infinity, you approach four-dimensional Minkowski space. All of these are very, very crucial observations for what we're about to do. Okay, the last observation is that, and I won't ask a question about this. This geometry is S2 foliated. So what that means is that if you fix the value of the radius and you fix the value of t, and you just move in theta and phi, you'll sweep out the surface of a two-sphere. Okay, so it's a lot like the Schwarzschild solution, essentially. Any questions about those three observations? Good. Okay. So what we're going to do is we're going to make use of this to just freeze time. Because if the geometry is not evolving in time, and you're trying to figure out what the hell's going on, if it's not changing in time, just say, let's fix time and look at the spatial geometry. So it's like taking a picture, okay? And if you kind of know what's going on with the spatial geometry, then if you let it evolve with time, it doesn't do anything, it just sits there, okay? So we're going to freeze t, and when we freeze t, that of course leaves us with dr squared plus r squared plus b squared, and yeah, we'll go ahead and call this d theta squared plus sine squared theta, d phi squared. Okay, so now, how many dimensions is this geometry?
3.
It's three-dimensional. It's r theta phi. If you haven't figured it out by now, we are severely handicapped in our ability to visualize three-dimensional geometries. Okay? We live in three spatial dimensions. And so when you try to visualize what a different three spatial dimension geometry looks like, you just kind of can't. So the trick that we use is we take the geometry we want to study and we want to reduce it to two-dimensional and then embed it in three dimensions so that you can kind of think about the height as representing the curvature. So you've all seen this. You know, one way to talk about gravity as the curvature of space-time is to draw some picture like this. Everybody seen that? Okay. This is supposed to represent a 2D geometry, but you're representing the curvature by allowing that 2D geometry to be deformed in the third dimension. You do not need the third dimension. This geometry is completely well defined in 2 dimensions. It's just hard to visualize the curvature. Okay? But we're going to make use of this trick in studying that geometry. So we want to take this thing and reduce it to 2 dimensions so that we can embed it in 3 dimensions and sort of use height in the third dimension as a proxy for curvature. All right? So to do that, we are going to pick on an angular coordinate. So we're going to set theta equals pi over 2. Okay, so we're going to take the polar angle, which we know takes us from the north pole to the south pole in spherical polar coordinates, and we're just going to fix it at pi over 2. All right. One of the reasons why we would pick something like the pi over 2, the equator, instead of the north or south pole is in the north or south pole, phi becomes sort of useless. So pi over 2 is just nice equatorial, and when we do that, clearly the d theta squared term disappears and the sine squared theta term just becomes 1. And so now we have d phi squared. And at the end of this story, we can come back and restore this. But just to give you a visual, what we're doing is we're taking these two spheres and we are replacing them by an S1. So setting theta equals pi over 2 just means that you're taking the equatorial circle and you're letting that be the only part of that two-dimensional space that's left. So now this is a two-dimensional space, coordinatized by r and phi. Right? Okay, so what we want to do now is we want to stick this bad boy in 3 dimensions. So if we're going to stick this in 3 dimensions, we're going to take this and we're going to embed it in R3. Because that's the space we think about when we think about 3 spatial dimensions. Okay, don't want to throw time back in the story. However, it's probably obvious at some level that if we're going to set up coordinates in R3 to help us with this embedding, that cylindrical coordinates might be naturally adapted to this because it's already got a distance, a radial part, and it's got an angular part. And all we're doing is adding in the 3rd dimension. So if we use cylindrical coordinates, we can keep a radial, keep an angular part, and then we just add in a z. So what I'm going to use is a z-axis, a rho axis, and an angular coordinate psi. And then I'm going to identify how each of these are related to r and phi.
If we're using z to sort of add theta back, do we not have to think about the fact that theta only runs for a certain number of angles and then sort of repeats on
Wait,
itself?
we're going to use z to add theta back? No, we're not. Theta will come back at the very, very end,
Okay.
but you'll never be able to visualize what happens because you're going to, I'll tell you why
Okay.
when we get there. Okay, so the metric of flat 3-dimensional space in cylindrical coordinates, what do you think it looks like? No. You do. What do you think the metric of flat space looks like in cylindrical coordinates?
dz squared, rho squared, d rho squared.
Sorry, say it again?
I said rho squared, d rho squared, but I think I'm wrong.
So rho is a length. So if you do rho squared, d rho squared, it's like length to the 4th.
No.
So usually rho squared is in front of an angle squared.
Okay, so rho squared, and then some dependence on side, probably.
So cylindrical coordinates are just regular polar coordinates appended with a flat or dz direction.
Okay.
So what does just the polar coordinates of a plane look like?
I should know this one.
It's okay. Danielle can help you. So what's the metric in 2-dimensional polar coordinates?
It's 1 and then sine squared theta dv. So that would be
D rho squared plus rho squared times d psi squared.
Yeah, you guys are working in too many dimensions. This is literally 2 dimensions, so it's the sort of easiest one.
yeah.
So in polar coordinates, the metric is just dr squared plus r squared d theta squared. I'm relabeling them. And then this is just adding on a z direction, the axis of the cylinder. Okay? Now, what we want to do is to embed this geometry in this geometry. What we need to specify is the positions in this geometry of the points on this surface. That is, what are the z positions as a function of r and phi? What are the rho positions as a function of r and phi? And what are the psi positions as a function of r and phi? So there are three functions that I need that tell me how each point on this geometry gets mapped into R3 in this particular coordinate system. Okay? And it's probably reasonably obvious that if this is an angular coordinate that goes 0 to 2 pi, and we're using this as the angular coordinate in R3, if I align the z-axis perpendicular to the r-axis here, then I can identify basically psi and phi to be the same thing. I don't have to do that, but you really want to, because it would be like the following. It would be like an E&M problem where we gave you a cylinder of charge, okay? An infinite cylinder of charge that looked like that. And then you said, okay, I'm going to work this in cylindrical coordinates where the z-axis is here and the rho axis is here and the angle goes like that. Okay? It's true, it's a cylindrical geometry and you're using cylindrical coordinates, but you are doing not yourself or anyone else a favor by not aligning them. So all we're doing is we're aligning these two cylinders. All right? So with that in mind, this is just going to become phi. And so really all we have to do is figure out what the z of r and the rho of r are. Okay, so one way that we can figure this out is we can take this metric and we can rewrite it in the following form. And now what I want to do is I want this metric and this metric to agree. And by demanding that these two metrics agree, I'm going to be able to extricate these functions, which these are no longer functions of phi because we've aligned our coordinate axes, and so we would expect azimuthal symmetry for these coordinates. Okay? So, well, let's look at it for a second. So I've got dz dr squared plus d rho dr squared times dr squared plus rho squared d phi squared. And then if I compare that to this guy, what do I need this combination to come out to be? 1. And what do I need rho squared to be? R squared plus b squared. Exactly. So if rho squared is r squared plus b squared, then I can immediately from that, yeah, we'll do it here, calculate d rho dr, and d rho dr will come out to be r over the square root of r squared plus b squared. Okay, just solve that for rho, take the square root of both sides, and then take the derivative of rho with respect to r. Okay, I need that because it appears there, right? And then, remember, our other condition is that those things have to add to 1. So dz dr squared plus d rho dr squared. That noise is just driving me up the frickin' wall. Becomes the following. It becomes dz dr squared plus r squared over r squared plus b squared equals 1. Okay? Does everybody understand the steps I'm following? I'm going nuts with that noise. Does everybody understand this? It's off. I turned it off. I muted it. I've tried everything up here.
It's something in the room's above us.
Yeah, awesome. That's great.
Do you want someone to run upstairs?
No, I'm good. I'm good.
Are you sure? You seem really
I'm
angry.
really. It's driving me nuts.
You do seem very upset.
We could just go, we could just go, balance it out.
What? Yeah. I always love the idea of negative frequencies, canceling out the positive frequencies.
Where does the energy go?
Okay, so at this point, if I'm really interested in the function rho, by the way, rho of r I have, okay, you just take the square root of that, so I'm done with that. I've identified this. The only other function I'm looking for is z of r. Can I get z of r from that? Yeah, what is that? What is this thing? It's a differential equation. You have to solve it for z of r, okay? I'm just going to give you a solution, but that's what this is. So you have to at some point do a differential, solve a differential equation. And if you solve it for z of r, you find the obvious solution that this is the inverse sinh of r over b times b. And this is having chosen z of 0 to be 0. Okay, you obviously have a boundary condition when you solve a differential equation. And in terms of rho, which is actually going to turn out to be useful, this is just b inverse sinh of square root rho squared over b squared minus 1.
How do you know that z at 0 should be 0 for your initial condition?
It doesn't matter. You're literally just picking. So there's an isometry along the z-axis, and so I'm just saying, like, this is, you know, this is how I'm defining z equals 0. Z equals 0 is utterly unimportant. But I have to. There's a condition that I have to pick at some point.
But if you're going to be graphing this in R3, is it setting like z?
I'll show you when I graph it what the condition, what changing that condition would change, and you'll be like, oh, okay, cool. Madison.
Yeah, just to clarify, that's like rho squared b over b squared quantity minus 1, or is that minus
Yeah.
to the denominator?
No, yeah, sorry, it's quantity minus 1.
Okay.
Which you could get by taking this expression,
Yeah.
solving it for r, and plugging it in right there. Okay, all right. Now, one thing to notice from this expression, which might not be obvious, but if you kind of dug into what you know about hyperbolic trig functions, is that for r greater than 0, which is of course the restriction on our coordinate range, z is greater than 0. Okay. So if you just study how inverse sinh of r varies with r, you'll discover that for positive values of r, that z value is going to be positive. All right, here we go. You ready? You're going to love it. I promise. Let's get rid of this. So what I'm going to do is in R3, I'm going to plot the surface that I'm trying to describe. So that's my z-axis. And to make life simple, I'm going to scale z by a factor of 1 over b. Okay? And this is going to be my rho over b axis. We could have just set b equals to 1 in this analysis, but you know, keeping b arbitrary kind of lets you see the effect of shifting b. All right, so there is a special point, say right there, where rho is equal to b, or alternatively, if you're talking about positions r is equal to 0. Oh, I thought you brought dog treats. I was like, really, we're gonna do this? Okay, and now I'm just going to plot z as a function of rho, because we've got this function right here. Okay, but I only get positive values of it, and so if I plot this thing, it looks like this. Right? Now, there's a symmetry in the azimuthal angle phi. So really the way I need to understand this picture is that I revolve it around the z-axis. So for example, this point becomes a circle. Okay. This is the natural embedding of the space described by this metric when we've frozen time and we've just set theta equal to pi over 2. This is what that surface looks like when I embed it in 3 dimensions. Okay? Interesting. Now, if you want to go back and try and visualize what the actual 3-dimensional space looks like, then all you have to do is everywhere I've got a circle here, you go back and replace it with a 2-sphere, which of course you can't visualize. But that's how you would undo this step. You identify where your circles are, and then to go back to the full 3-dimensional spatial geometry, you restore those to spheres. Okay? But we're not really interested in that right now. Now this space has a property which is incredibly important to observe, and is a property we call geodesic incompleteness. What do I mean by that? What I mean by that is, on this geometry, we would have the geodesic equation, because we have a metric. We can crunch it through the Mathematica package, get the Christoffel connections, write down the form of the geodesic equation, and then we could pick a point in the space, give you an initial path or an initial velocity, so initial position and initial velocity, solve the geodesic equation, and then that would just tell us the trajectory of something responding to this curved geometry. Okay? Yeah, go ahead.
I don't know if I should bring this up now, or you can talk about it later if you want, but I was just curious about the limit as b approaches 0, how it goes to flat space, like the visualization of that going to flat space.
Yeah, so the visualization of that is that as b goes to 0, this thing closes up.
Then you get a cusp.
No, you don't get a cusp because in the...
Would the wings then also kind of like flatten out?
Yeah, so you're...
Like I said, you don't have to answer it now. If you
yeah, yeah, it's a little wonky, because the reason you're thinking that you have a cusp is because you're thinking in terms of the circles closing up, but they're spheres. And so what you have is if you take b to 0, this thing comes to a point, but at that point there's a zero radius sphere, but as soon as you move a little bit away, those spheres grow, and in fact you just grow this into R3 in spherical polar coordinates.
Why would it go, like why would it shrink? Because if b is going to 0, wouldn't that make rho and z go out?
Well, this point is when rho equals b.
Okay.
So if you're taking b to 0, then
okay.
on the rho axis, that is when. But let me. So you're absolutely correct that this entire story, when b is equal to 0, should just reproduce the story of flat space in spherical polar coordinates or in cylindrical coordinates. Okay. But for now, let me come back to this geodesic situation. So there are 3 classes of geodesics that you can think about in this space. One is, if you set things up just right, you can have a geodesic which is periodic. That is, this thing is just going to make laps. Okay? You can also have geodesics which are infinite, in the sense that they might do something like this. And it's important that when you talk about an infinite geodesic, it has to be infinite in both directions of propagation. So you might start it out going that way, but you also have to be able to talk about where it came from. That's a truly complete geodesic. It either has no beginning and no end, or it's periodic. But of course, we can easily see that we can pick a geodesic in this space that is finite, because it might go back infinitely in that direction, but when it hits this point, it stops. So any geodesic which is sort of aimed downwards enough is going to hit this circle, and it ends, because there's nowhere, the 2-dimensional space ends at this circle. There's nowhere for it to go. If you started with the geodesic aimed away, it could move away for infinity, but if you track it backwards, it ends in the past. So when a space has geodesics which terminate, then that space is called geodesically incomplete. And one of the very interesting things about this, which I only learned the last time I taught this course, is that geodesic termination is actually the most broad way to define a singularity. So if you think about a black hole, the singularity at the center of a black hole is the place in space-time where geodesics terminate. Because if you start with a geodesic out here, once it gets there, it stops. Things like that don't exist in space outside of the presence of singularities. Okay? Go ahead.
So does that imply like this geometry describes a singularity that is larger, like a possibly bigger, like?
Well, yeah. You could say that. So one way, so there are two ways to absolve this situation. Okay, one is to do the same thing that we do with a black hole, which I secretly haven't told you, and that is to make a black hole consistent with general relativity, we simply remove the singularity at the center. What? Because if you remove, just bear with me, if you remove that point of space, then you can approach it infinitely. You never get there. And if this is an idea which is kind of lost on you, come to my lecture next Wednesday and I'll show you what I'm talking about. But if we remove that point of space, then these geodesics do not end. Similarly, we could remove this circle. So if you're not familiar with what I'm saying, I mean, I think the more mathematically comfortable people in the room are on board with this. So if I think about a sphere, S2, and I think about the volume inside, okay? As long as the actual surface S2 is there, if you're inside, you can move outwards and then bang, hit the surface. But I can define a space which is only the interior of S2, where I do not include the surface itself. So this includes points in the volume of the sphere, but not the surface itself, which means that as you move closer and closer to the edge, there's always points in front of you, because you don't actually have the ability to hit the edge itself. Go ahead, Ryan.
So in like our actual universe, if singularities don't exist, we are geodesically
complete. Geodesics could run forever. And you might get confused. You might be like, well, if I jump off a building, my geodesic's going down, but when I hit the ground, my geodesic terminates. But it doesn't, because if you're sitting at rest on the ground, you're still moving in time. This is where the geodesic at the center of a black hole is such a mind truck. Because when you hit the singularity at the center of a black hole, you're no longer evolving with time either. It's kind of mind-blowing. You probably wish I'd give a public lecture on black holes, but I'm not going to. Anyway.
So you're saying instead of hitting the singularity, you're asymptotically approaching it?
Yes.
Okay.
If you remove the singularity, if you remove the singular point. Okay, that is not what I want to do though. God damn it, I really like my circle. I drew a really nice circle there.
That's pretty good.
How can I save my space? What can I do?
Keep going.
Yes, exactly. What if we just took our space and continued it?
Is it a wormhole or a white hole?
Okay. Now, the key to understanding what's going on, and I want to make this clear, to save the geodesic completeness of the space, I have extended it to include something that wasn't there before. Yes?
Why do we need geodesic completeness?
Well, otherwise you're introducing singularities into the space that you can't explain. I mean, if it's not geodesically complete, then the geodesics are terminating. They're terminating on these things which we generically call singularities, and we would like to avoid them if possible. Okay? Now, for the region up here, so mathematically, how would we do this? Well, up here, we're basically looking at the regions where R is positive, because I said whenever R is positive, that's telling me that I'm working with a z being positive. So these are the original r coordinates. To extend the space to this lower sort of piece, all we do is we take the radial coordinate in our original coordinate system and we allow it to run negative. Because if I let r run negative, then the z values become negative and they mirror what you have in the positive case. Okay? So mathematically, the description of the bottom half of this looks almost identical to the top. All right. If we go to r equals infinity, then this space asymptotes if we restore all of the other dimensions and everything to M4. If we take r to minus infinity, then the bottom also asymptotes to M4. But these are two different asymptotic spaces. To get from this asymptotic flat space to this asymptotic flat space, you have to go through r equals 0 and down to negative infinity. Okay? This is, as someone suggested, an example of a wormhole. Okay. It's not the kind of wormhole which you normally see in science fiction movies. In science fiction movies, the wormholes are handles on a geometry. So you have like flat space, and then you have some region where you introduce a handle. Okay, so this is, it's a tube. And you can enter here and get out here without having traversed through there. Okay? So, I think this is the kind of wormhole they talk about in Interstellar and other movies where you're in space, you enter the wormhole, and then the wormhole pops you out somewhere else in space. That is not what this is describing. This is describing two asymptotic and distinct spaces that are connected by a tube, or a throat, as it's called in the typical applications. So if you tried to go through this thing, you would end up in a completely different space-time. Right? Now, this might excite you because these are smooth geometries. Okay? When we connect this thing and we actually look at the curvature tensor as we move around this geometry, it never blows up to infinity. You could kind of guess that because it's just nice and smooth. It's like a curvy tube and it's not got any kinks or weirdness. Nothing's getting shrunk down to a point. So this is a smooth geometry, and that means that it would actually be reasonable for you to move through the wormhole throat. Okay? There's just one bad thing about these particular wormholes. To create a geometry like this requires a negative energy density. Okay, that's not obvious, just take my word for it. But to create a wormhole geometry of this form requires negative energy density. Now, where can we get negative energy density from? Are you negative energy density? Say again? So all of the stuff, the people, the atoms, the stars, the planets, those are all positive energy. The energy density you can just think of as like a mass density to first order. Mass is positive. So almost every normal source of energy that we think of is going to be a positive energy density. The only way to get a negative energy density is from a vacuum energy, which is also what corresponds to the dark energy in the universe. Okay? Now, vacuum energy, unfortunately, only comes in two varieties. It is either constant and uniform, which is how we think of dark energy. But if it's completely uniform, it's not really capable of generating a localized thing. Because after all, this is a throat, it exists maybe here. Well, how do you decide it exists here when dark energy is uniform everywhere? What you need is localized negative energy density. But the only other form of negative energy density at our disposal is quantum fluctuations. But quantum fluctuations are small. Which means that if a wormhole like this ever existed, it would be very tiny, on the order of a quantum effect, which means that you can't go through it. Jonathan?
How do we know that dark energy is uniform?
for reasons we'll talk about when we get to cosmology. We're going to do cosmology at the end of the semester. We're going to talk about where dark energy comes from.
Oh, great.
But that's the big difference between dark energy and dark matter. Dark matter clumps. So dark matter is stuff like, you know, the stuff we're made of, so it actually gravitationally, you know, clusters, but dark energy is uniform. That's the key difference, which I don't feel like people elucidate on a very regular basis. And dark energy can be positive or negative. Dark matter, positive energy density. Okay. All right, so that was a warm-up. Now we're going to do the real thing. So, without any further ado, let's get back to black holes.
I thought you said this wasn't going to be a lecture on black holes today.
No, I said that. No. I said my public lecture is not going to be a lecture on black holes. No, of course we're doing black holes in this class. No, sorry. No, my public lecture was supposed to happen yesterday. And yesterday was when the photo of the black hole was released, and so everybody was like, "Oh, it's such great timing because Flournoy is going to give a lecture on black holes the day the black." And I'm like, "No, Flournoy is not going to give a lecture on black holes." Okay. So let's go back to our friend the black hole. Shit, that's a lot of pages of notes. This is. So we're going to go back to the Schwarzschild geometry. And we're working, of course, in Schwarzschild coordinates. God! T, R, theta, phi. And we're only going to work with radial coordinates outside of the horizon because, as we talked about last time, if we're dealing with Schwarzschild coordinates, you can't really connect outside of the horizon to inside of the horizon. That's why we introduced Eddington-Finkelstein, but we're not going to use Eddington-Finkelstein today. We're going to introduce yet a new set of coordinates. Okay, so to investigate whether or not this space is geodesically complete, we are going to make use of the following new and gooder coordinates. Capital T, 1. Capital R, 1. T is going to be our new time coordinate. R is going to be our new radial coordinate. 1 will make sense later on. So here we go. Here's our coordinate redefinitions. Okay? Pretty simple, right? Yeah, no, nobody gets famous for doing anything easy, I'll tell you that. Right? There you go. Couldn't be any harder. Now, there's actually a lot of power in this particular coordinate redefinition, and the way that these things are usually derived is done in steps, but I'm just going to go straight for the throat. These are what are called Kruskal coordinates. Capital T, capital R are the Kruskal coordinates. So the first thing that we should investigate is, with this new set of coordinates, what are the ranges of these coordinates? Now this is all based on the ranges of the coordinates we're starting with. So T goes from minus infinity to infinity, R goes from 0 to infinity, and then theta and phi do the usual angular thing. Okay? So if you take the allowed values of T and R and you plug them in here and ask what are the allowed values of capital T and capital R, what you discover is that T sits on minus infinity to infinity, just like the ordinary time, and Ri sits on 0 to infinity, but it doesn't include 0. Now, the metric we get just by solving these for r and t, and then taking derivatives and plugging them into the Schwarzschild metric. I'll spare you the details, but if we do that, then the metric in these coordinates takes the following form. And I'm kind of mixing my notation here. So I'm leaving in places where it's convenient, I'm leaving in the Schwarzschild radius. But in particular, I'm writing my coordinate differentials in terms of the new Kruskal coordinates. So the reason I'm doing this, normally you would just go whole hog. You would write everything in terms of t and r, and just not have little r and little t anywhere. But what's nice about doing this is, when we think about the black hole, the first time we got to it, we were describing the black hole geometry in terms of r, where we know that r equals 2gm is where the shit hit the fan. Or actually, that's actually okay. This is where the shit hit the fan. So by leaving in the little r dependence, we can talk about what's happening to the geometry by referencing familiar points in this picture. If I just wrote it purely in terms of capital R, you'd have to figure out, well, what value of capital R corresponds to the horizon, blah, 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 blah. So this is just giving us a way to use what we already know about the positions along the radial direction where interesting and very cool stuff is happening. Okay. Okay. All right. There are three very important aspects to this story with the Kruskal coordinates. And the first is that lines of constant r, so that is if you want to sit at a fixed radial position with respect to the black hole, lines of constant r satisfy the following. Okay? If I take a line of constant r, then that means that this whole coefficient is constant and this whole coefficient is constant. But if I square this and subtract the square of this, I just got good old cos squared minus sin squared. We've got a hyperbolic trig identity for that. And so you can argue to yourself that lines of constant little r satisfy this equation. Okay? Where the sign of the term in parentheses, Avery is not here. Will, what is the sign of the term in parentheses?
Your R is positive, right?
Your R is positive. Actually, I mistakenly quoted what Gabriel said earlier when I was talking about coordinate ranges. So earlier I was saying we use these coordinate ranges to figure out these coordinate ranges, and I said what's the range of t, and you said minus infinity to infinity, and then I said what's the range of r, and you said 0 to infinity. No. You only use 2gm to infinity. The Schwarzschild radius is only good outside of the black hole. Okay? So given that r is bigger than 2gm, what's the sign of this?
Negative.
It's negative. Okay? It's multiplying an exponential, so the right-hand side of this is negative. So this probably tells you that in the t r plane, what shape is that describing? Remember, we're taking a constant r, so the right-hand side is constant, it's negative. What kind of shape is that describing? What do you call it? It's a hyperbola, right. Okay, so we've got the right branch of a hyperbola. Do this. All right. For r equals 2gm, that is the smallest value of r, what is the right-hand side? 0. It's 0. Okay. So for little r equals 2gm, which means you're at the horizon, we actually have that t1 squared minus r1 squared is equal to 0. Which of course means that t1 is equal to plus or minus r1. which means that we have these asymptotes at 45 degrees. Okay, so let me identify some things here. So this asymptote is r equals 2 gm up there and down here. And then this is a line of constant r, but not equal to 2 gm. Okay. So if you take a fixed r that's not at the horizon and you just follow it in this time coordinate, in the far future it actually asymptotically approaches the horizon in these coordinates, or if you go to negative infinity. So you can think of this as t equals infinity or t equals minus infinity. Okay? Now you can ask yourself, what do lines of constant t look like?
Hey, Alex.
Yeah, go ahead.
John.
What's it called? How do we know they're lines instead of just t and r equal to 0? Because based on how little r is defined and how big r and big t are defined, don't big T and big R just end up as 0?
Sorry.
So based on the definition of like crucible coordinates,
Yeah.
t and r1 should both be equal to 0 when r is equal to 2 gm.
T and R1.
T1 and r1.
By those
give the
first
definition.
definitions, if you
Yes.
plug in r, that
R
first
over 2
term would
gm
be
minus
0.
1. That's 0 when r is equal to 2 gm. So there should be points, not lines, with asymptotes.
Yes, when r is equal to 2 gm.
Is it maybe because R can't be 2 gm, but it only approach 2 gm?
Oh wait. Oh yeah, because we defined it that r can't.
Yeah, R can't
It's
actually be 2
bigger than
gm.
it's never.
It has to
Yeah,
be
yeah. So this is, yeah, so you're right. This is what it's approaching as r approaches 2 gm. Okay, not explicitly at the value of 2 gm. Yes, thank you. Okay, so if we now do lines of constant t, then we want to allow r to vary, but then the sense and the cost are going to be fixed. And so we immediately find that in order to get rid of the r dependence, we can just divide this thing through. And so we find that t1 is just hyperbolic tanh of t over 4 gm times r1. Okay, so how does t depend on r for constant time little t? What is this describing?
A line?
It's describing a line through the origin. Okay, so lines of constant time are just lines emanating from the origin. Okay. So this is a weird set of coordinates, right? Very, very different than what we're used to, but it's going to prove powerful in just a minute. All right, third observation, which is probably the most important of all the observations I'm going to make. If I ignore angular motion, and I want to study causality like we did for the black hole, the Schwarzschild and Eddington-Finkelstein coordinates, we ignored angular motion and we just focused on radial motion. What did we study to talk about causality?
Light cones.
Light cones, exactly. So, for radial motion, that means I'm going to ignore this term in the metric. ds squared equals 0, which is how we define light cones, implies minus dt1 squared plus dr1 squared equals 0. Okay? If I'm going to draw this light cone, what is it going to look like? Well, I mean, this immediately tells me that dt1 over dr1 is equal to plus or minus 1. It's 45 degrees. But here's the amazing thing. Are you ready? This is why we do a weird coordinate transformation like this. That result doesn't care where you are. Even though lines of constant r are doing weird curvy shit, and lines of constant t are flying out all over the place, if you want to draw a light cone in this geometry at any point, you just open it at 45 degrees. And it doesn't matter where you are. Okay. That is actually a driving factor in how we decide certain coordinate transformations. It is to make the light cones uniform, because then you don't even have to draw them. When we did Eddington-Finkelstein and we were trying to talk about the light cones tipping over, you drew them because you wanted to see this interesting behavior. But if I can give you a coordinate system where the light cones everywhere look identical, you don't need to draw them because you just automatically know. So that is a huge advantage to this coordinate system, and it's going to be amazingly useful when we ask about geodesic completeness. Okay? So first observation. If I'm right here, I am of course free to move within my future light cone, but part of that involves migrating past the r equals 2 GM line. So if I want my space to be geodesically complete, I need to put something in the picture here. Because I certainly have geodesics that start in the region I'm studying that can wander into this region. Okay? So in order to accommodate that, what we're going to do is introduce a new set of coordinates. Don't worry, they're going to be intimately related to what we already have. All right, I'll do it up here. Okay, so our new coordinates will be the following. T2 and R2, where T2 and R2 are defined as follows. Okay? Very minor changes. So this was the form of the metric in my original Kruskal coordinates that are describing what's happening over here. Ready for this? Here's the form of the metric with these new Kruskal coordinates. Okay? Now, some things have changed. Lines of constant r satisfy an equation very similar to this, except, when I'm in this region, I'm at values of r that are less than 2 GM. So what is the sign of the term in parentheses? It's now positive. Because I'm trying to work in this region, which is where I've gotten after I've wandered past the line r equals 2 GM. So now, if I'm in the second region, this is positive. So a line of constant r satisfies this equation. Caleb, you want to guess what shape that's describing?
Parabola? Wait, hyperbola?
It is another branch of a hyperbola, but this time it's this way. Okay. Similarly, if I take r to be 2 GM, then the limit of these is this line right here. But here's something interesting. What about r equals 0? So we're inside of r equals 2gm, so we can certainly go down to r equals 0. If r is equal to 0, what does this thing become? What does the right-hand side become? It becomes 1. Okay? If I plot that, then it's literally one of the hyperbolas. It's actually the largest one. So that particular hyperbola branch is r equals 0, but r equals 0 is the singularity at the center of the black hole. So a line of constant r, say like this, would be r not equal to 0, but less than 2gm. So in this diagram, we've got some really weird stuff happening because what was a point-like singularity in these coordinates is turning into a branch of a hyperbola. Okay? Now here's the cool part. We got the same metric. We can talk about lines of constant time. They're still going to be described by straight lines. Okay? So lines of constant t are still going to be described by straight lines because this hasn't really changed. Light cones are still described by 45-degree openings. But check this out. God, that's a busy picture. Here, let me just draw a cleaner picture right here real quick. Let's talk about the light cones for a second. Okay? If you're outside of the black hole, then you have the freedom to wander away from the black hole, but you also have the freedom, should you choose, of passing through the horizon. However, once you are at the horizon or inside of the black hole, where does your future eventually end? At the singularity. So this diagram, as complicated as it's getting, is replicating everything we know that we talked about last time. That is, outside of the horizon, you are free to go away from the horizon or enter the horizon. But once you're inside of the horizon, which should have used colored markers, once you're inside of the horizon, your future is to meet the singularity at r equals 0. Okay? Are you ready? We would like to ask ourselves if this space is geodesically complete. And what I will pose to you is an event there whose light cones look like this. So I'm going to shoot photons, for example, from this point. These photons are happy to reach the singularity at the center of the black hole. These photons are happy to stay outside of the black hole and shoot away from it. But if I want to argue whether a space is geodesically complete, I have to think not just about the future of a path, but I also have to think about the past. The past of this path is fine, but the past of this path is going into a region of space-time that doesn't exist. There is nothing in our description of this geometry past this line. So what we're going to do is exactly what we did in the warm-up. We're going to extend the geometry. Okay? I could just remove this line, but then I am identifying it as a singularity. Instead of removing it, I'm just going to extend the space. So with that in mind, we will employ a coordinate redefinition for what we call T3. And the good news here is that these definitions are just opposite the definitions in region 2. So the definitions that I just used to define this region, I just use minus. And so what I discover is is that I now have a region like so. There is a limit to where I can go. Because everything satisfies basically the same equations. You're just flipping around where the arms of the hyperbolas are. This is again a singularity. Okay? But remember, the light cones still open up at 45 degrees. So if I am right here, I am free to move within my light cone. That means I am free to wander outside of this line. But once I'm outside of this line, for my future, I can never go back past that line. You can go past this line in your future, but once you're outside of this line, you can never go back. What do we call it? That's a white hole. So this is a white hole geometry, or I should say a white hole branch of this geometry. It has a singularity as well. So when you trace these paths back, they do end, but that's okay because we know there's legitimately a curvature singularity there. And you see this from looking at the light cones. This is a horizon, but it's the horizon of a white hole. So you can be within it and leave it, but once you're outside of it, you can never go back. So it's still a one-way surface. That's why we call it a horizon. It's just now it's a one-way exit instead of a one-way entrance. All right? We good? No, we're not good. Because we're not done. Because if I think about a light cone here, he is jetting off into some region of space-time which doesn't yet exist. I mean, this is within the space that I've drawn, but one leg of this light cone is shooting off over here. So without any further ado, T4, R4 are defined in terms of what we had in T1. And the whole story just repeats itself over here.
Is R4 negative R1?
Yes.
R5, yeah, sorry, there's negatives. Sorry. Okay. And hopefully at this point, I kind of went through it in detail for the R1, and then I did a little bit more detail in R2. But these minus signs, they really don't change things radically. For example, they don't radically change the light. They don't change the light cones at all. They don't really mess with the lines of constant time. The lines of constant R, well, it's just flip-flopping where your branches of the hyperbolas are. Okay? Now here's the thing. If you go way off over here to the right, that is getting way, way far away from the horizon, what kind of space do you eventually reach? Flat space. This is flat Minkowski space if you get way the hell away from this black hole. But guess what? If you go way, way, way far away from the horizon, and by the way, the horizon is this set of asymptotes. If you go way far away from that horizon, what should you asymptote to? Flat space. But it is a different flat space than this one. Yeah, go ahead.
So like the limits on the vertical axis is just undefined in space?
The limits on
After you pass the hyperbola on the upper...
This guy? Yeah, this doesn't exist because this would literally be, it would be like negative R, but we don't have to put a negative R in. I mean, we don't need anything here because geodesics can actually end on a singularity. That's legit. It's a real curvature singularity, okay? So what we have discovered is that by looking for geodesic completeness of the Schwarzschild geometry, then we have been forced to introduce and accept not just the black hole we started with, but a white hole and a second asymptotic universe. Well, of course, we have a universe, an asymptotic universe, and they're connected by this object. What do we call this configuration? It's a wormhole. Okay, so this is a wormhole induced by extending the Schwarzschild black hole solution. Now, this is an example of what is called a non-traversable wormhole, because you cannot get from one side, being outside of the black hole, to the other side. Because remember, to get from here to try and get over there, you're going to have to pass this line, which means you're going to end up dying at the singularity. Here's something you could do that's cool. Say you and your twin are born down here. You could investigate this universe, and your twin could investigate this universe, and then you could both choose to come inside this black hole and compare notes.
Die a beautiful death.
You would die a beautiful death.
How would you decide how to get back at the same time?
Say it again?
How would you decide how to get back at the same time?
Well, I'm not saying it'd be easy. So this is one of these. So this is what is called a maximal extension of the geometry. Now, I want to be realistic with you. Can this exist?
Yeah.
No. Why can't it exist? Well, go back to the very, very beginning of my story. I wrote this metric in these coordinates, and I said something about the values of t. What did I say? They are minus infinity to infinity. There are two realistic problems with that. Number one, the universe has a finite age. The universe doesn't go back to t equals minus infinity. Number two, the black holes that we know exist, the ones we take pictures of, were formed from stellar collapse. Saying that t goes from minus infinity to infinity is implying that this geometry has existed eternally. And there's no realistic black holes that are like that. Okay? In the notes that I'll put in the course website, I will actually draw the Kruskal diagram for a star that collapses. And it's a much more boring thing because you basically don't have any of this. You just have external, and then it morphs into the singular geometry in the center. Now, I don't want to deflate you, though, because on the one hand, while it is true that this story relies on something that we can't find out in the universe, physicists, and I am included in this, spend a lot of time studying these geometries. Because one of the things about general relativity that you have to understand is that for general relativity to be a consistent theory, it has to be consistent whether you're applying it to the particular scenario of our universe or whether you're applying it to any solution that it affords you. Well, this is a solution to general relativity. And we spend a lot of time exploring the consequences of general relativity, and in particular quantum gravity, on these maximally extended solutions. And we get a lot of really weird results out of it. Okay? So theoreticians play around with this a lot. And I've had like 4 senior design projects that have been playing around with these sort of maximally extended black holes. In the real world, in astrophysical applications, this is sort of a no-go. Okay? But I think it's really cool. That's it for today. Hope you had fun. We'll see you next time. Caleb, go for it.
Can a massless particle live from one side to the other?
Because it has to travel on the electron. So there's literally no way for you to get. I mean, you could in principle travel along this line, but that's not actually getting in there.
White holes actually exist. No?
There's no reason.
Okay. So there is no explanation in GR. That's white hole.
Well, no, what you're talking about is not just GR. In GR by itself, pure GR, there's these eternal solutions. But you're saying in the real world, is there something that might collapse?
Yeah.
Or But you're taking into account more than just VR. It's like when we talked about the stars burning out and collapsing. Like we were talking about a lot of different effects together. VR is one of them.
You totally have space time.
Turn the camera on.
Is this
M4
How do we do that?
sort of like the same as ours, but it